In this video, I want to start talking about the sampling distributions around proportions. Okay. First of all, a little review. The amount of money owed in student loans from a particular university is thought to be normally distributed with a mean of 12,300 and a standard deviation of 4,120. Let X be the amount of money owed by an individual student. Find the probability. Okay, I'm going to color code this a little bit. So here's my normal curve. It's normal. Mean is 12,300. Standard deviation is 4,120. Okay, so let's start with the black, or the probability that X is greater than 20,000. We'll do this one in red. Okay, so here at 20,000 and greater, so we'll shade that up. Okay, for less than 15,000, so maybe we put the 15. Let's do this one in blue. 15,000 right here. And we'll shade down. And between 10,000 and 12,000, we'll do this one in green. So let's do 10 and 12. And so remember, when you're showing your work, you want to state that it's normal. State the condition or the settings. By that I mean the mean and standard deviation. Draw the curve and then make sure and label the the ones that you're going to type in and the ones of interest, and then shade. I just put the answers in there for my calculator. I'm thinking probably we've done this enough. You don't necessarily need a reminder of how to type these things in, but you can always pause and take a look and make sure you're typing them in correctly. But let's move on. In a previous video, we talked about sampling distributions, and I'd run a simulation of rolling a dice 15 times and counting the number of ones and twos. And of course, in our head, we say, well, that should happen a third of the time. So you should get 5 ones or twos. And I ran that 500 times. I used Tinkerplots. I ran a simulation with 500 sample proportions. I plotted them. These were my sample proportions. We call them p-hats. And I found the mean, and you can see it was centered around that 33%, okay, or one third of the time. And sampling distributions, this is maybe an obvious piece, but we should know where our p-hats will be centered. In our heads, we know that a third of the time I should get a 1 or a 2. So if I took a bunch of samples, then that should, I don't expect to get a third every time, but I expect that to be the center of the distribution. More interesting is, how do we talk about the variability of this distribution? And that's what we're going to talk about today. So I'm going to use an example here. Suppose 85% of all dog owners will feed their pet a special diet at some point in their life. In a simple random sample of 150 dog owners, what's the probability that you find less than 80%? So what we found, in that previous slide showed, is with sampling, we think of it being a normal distribution around that, proportion that we knew for us in that previous example, that 1/3 mark. It should be centered around that, and it's going to look normal. So I want you to just think about this kind of idea in your head for a minute. We picture this normal curve. And for us, if it's really true that 85% will feed their dog that special diet, that should be the center of our distribution. And of course, depending on the sample we take, we might be off from that, but that should be the center. And we're saying, well, what if we got a p-hat? Okay, this is our p-hat because it was from the sample we took of 0.8. Okay, so we're missing one thing. We're missing a measure of deviation. Okay? Let's talk about how we can deal with that. Whenever we do something with a sampling distribution, we need to really check 3 conditions. One is kind of just an intrinsic built-in condition, that we should always be thinking about, and that is that we took a good sample. You know, we got a simple random sample, and we collected good data. Obviously, all bets are off if we collected the data in a bad way, right? So if we collected a sample of n, population size big N, the mean of our distribution should be the original proportion. And we talked about that already. It was 1/3, or 0.33 for our example with the dice. For our example that we're working on right now, it's 0.85. If it's 85% of dog owners, our samples of proportion should be centered around that. We expect some variability, but that should be the center. The standard deviation is given by this. You can see it's a modification of that kind of binomial setting we've talked about, but this is the deviation. As long as the 10% condition is satisfied. So this is, like I said, this is kind of the built-in, we need good data condition, but this is the first condition, that the sample size is less than 1/10 the population size. And this always feels like a weird condition because it feels, and it truly is, an insurance that our sample size wasn't big in terms of the population size. And people will say, but I thought big samples were better. And that's true. But remember that we're talking about proportions. So if I have, let's say, just a small population, let's say I go to a town of 1,500 people, and I say, I'm going to ask all 1,500 a question. Well, if I ask everybody, there's no variability in the proportion. I know the proportion. I asked everyone. So this is ensuring that I'm asking a small enough chunk that variability exists. On the other hand, we also want to make sure that the sample size is large enough that we can assume normality. Okay, and this is that condition. That's condition 2. And it really is just a function of, is the sample size large enough with the proportion we're talking about that we can assume normal. So let's just think about this in our example. Condition 1, I had 150 dog owners. Is that less than or equal to 1/10 the population of all dog owners? Of course it is, right? So we fulfill that. So we will be able to calculate the deviation. And the second one, our sample size multiplied by the proportion, and in this case, notice it's P, it's the center of our distribution, what we thought was true, and 150 times the complement of that. So this, if you calculate it, was 127.5. This, if you calculate it, is 22.5. Both of those are larger than 10. By the way, on the AP exam, you can't just say it's larger than 10. You actually do need to calculate what that is. So we have also fulfilled condition 2. All right, let's go back to the problem then and actually solve it. So this is the same exact problem. The sampling distribution, it's because of the large sample size, because conditions 1 and 2 were met. I'm going to put 2 little check marks. Because conditions 1 and 2 were met on the previous page here, we're going to say it's normal. And the settings were a mean of 0.85 and a deviation. Let me bring it out so you can see that I calculated it. Here it is. I also wanted to just call your attention to the fact I calculated it here, 0.029. I also stored it. If you've never done that, you press the store button. It's right above the on, and it brings you a little arrow, and then you can use your alpha key to assign it a letter. And that way I won't have to type in this thing, and it won't even round, right? I'll store the whole thing. It's kind of a nice way to do this. So I said 0.029. You could actually, right here, I'm going to write it out once. And then from here on out, I'll just round. But let me write it. Okay? All right, so what's the probability that our sample, we said, was less than 80%? Okay, so remember, normal, 0.85, 0.029, and there was 0.8, and we shade. Okay? The next question, I did calculate this, but let me do some writing and then I'll drag all the calculations out at once. The next one is more than 88. So here we again have the same normal 0.85, 0.029. By the way, it is nice to, if you have the time to just keep writing the standard deviation so you don't round, but in the interest of time here, I'm going to just round 0.88 and shade up. And finally, what's the probability that the sample finds a proportion within 0.02 of the original data? So now, within 0.02, of course, we've still got the same normal setting. I'm just going to leave it blank, okay, for just a second, because I know that I'm running a little long here. Within 0.02, okay, of the original data. So let me pull in the solutions here. So there's the solution for less than 0.8. Here's the final solution right there. So again, you can see I did from negative 1E99 up to 0.8, 0.85, and then I just put A there. Okay, same thing here. Same thing here. And you can look at my work. So nothing really new with the calculations. So again, the idea here is that samples have less variability than individual observations. And this is how we're going to begin to work. We're going to be judging, was a sample good, bad? Was it a probable sample or improbable sample? Make sure when you're writing these that you're, checking your two conditions. That kind of, first condition is, yes, it was a simple random sample. Was the sample size less than 1/10 the population size? And NP, n times 1 minus p, greater than or equal to 10. Check your conditions, and remember to show your work, right? And it is nice here, as I said, to just write that standard deviation formula again, because then it's not rounded.